Hello and welcome to this module 23 of manufacturing systems technology. A quick recap of what we did in the last lecture. We were talking about the various optimization conditions for optimizing the cutting velocity, and in that sense we had evaluated two different models. One was the optimum cost model and another was the minimum time or the maximum production rate model. And there we could report the velocities as one of the end conditions of CAP really, which had different steps, and starting with the analysis of part requirements, selection of raw workpiece, after that determining the manufacturing operations and their sequences, finally the selection of the machine tools using process capability analysis, selecting the toolings, the tool holders, etc., and the final step of that process plan was about determining the optimum machining conditions, which we were kind of reviewing. So here I would just like to illustrate that the modality that came out really in this process was there were two set of conditions. One was considering the minimum cost per piece, where the V minimum or the velocity corresponding to the minimum cost piece was derived to be this expression C divided by 1 by n minus 1 times of C0 Td plus C1 divided by C0 whole to the power of n. And here obviously the various terms, C for example was the Taylor constant and the tool life equation. So n is the exponential index of the Taylor equation. You remember the equation was Vt to the power n was equal to the constant C. C0 was considered to be the overhead and labor cost Td was the total time needed to replace a cutting edge, and C1 was the total tooling cost. Obviously T was the tool life, V was the cutting velocity in this condition, and C was a constant. So having said that, this was one of the criteria for determining the optimum machining velocity, for which the total tool life corresponding to minimum cost came out to be 1 by n minus 1 times of C0 Td plus C1 divided by C0. And the other criteria that was used was based on maximum production rate, assuming minimum processing time of the particular part, where the total estimated velocity, we call it V max, came out to be close to about this formulation C divided by 1 by n minus 1 times of Td to the power of n. And similarly the tool life corresponding to the maximum production rate condition came out to be 1 by n minus 1, and this minus 1 actually is in the numerator. So n minus 1 times of the total time needed to replace a cutting edge, which is about Td. So having said that, now the lead time which comes into picture, assuming that the lot size is of q units, would be really represented with this equation: lead time equal to whatever is the setup time. Let us say the major setup time associated with the process is some value, we can call it probably Ts, plus the amount of time of processing for one component, amount of cutting time, which we call Tu, times of the lot size q. So that is how you actually calculate the average lead time in this particular case. So we want to now apply all these criteria to determine the optimum machining condition, particularly the velocity or the time corresponding to minimum cost per piece model or that corresponding to the maximum production rate per model in a practical situation. So let us look at a problem example that I have formulated here for you. So you have a lot of 500 units of steel rods about 30 centimeter long, 6 centimeter in diameter, and it's turned on a NC lathe, numerical control lathe, at a feed rate given as 0.2 mm per revolution, and of course a depth of cut of equal to about 1 mm or so. The tool life data is given by this equation Vt to the power of 0.20 equal to 200, meaning thereby that the tool constant is 200 and the exponential in the tool life is about 0.20. The other data that are given are the machine labor rate, which is about $10 an hour, machine overhead rate, which is 50% of the labor rate. So basically labor plus overhead comes out to be about $15 in 1 hour, and so is the grinding labor rate, because you obviously need to first take the tool to its complete life by grinding and regrinding the tool and using multiple number of times till the edge becomes ungrindable. That is the whole logic used in all the machining examples or all these machining paradigms. So here also the grinding labor rate comes out to be about same $10 an hour with a 50% overhead charge, meaning thereby the labor and overhead combined for grinding also is about $15 an hour. And we have some other parameters of importance which would be enabling us to determine the optimum tool life, considering the minimum cost of the maximum production rate model and so on, also the optimum velocity conditions, so on and so forth. So we have the workpiece loading unloading time given as 0.50 minutes per piece, and there are some other data related to the tools. Mostly the brazed inserts are the tools which are the toolings which are used in this particular case. Remember, it is an NC lathe, so you will have to have multiple toolings and a single check with multiple toolings to do all the machining operation. The original cost of the tool comes out to be about $27.96, and the grinding time of 2 minutes is recorded per cutting edge, meaning thereby that before a tool replacement is on, before a complete tool replacement initiates, there are few steps of multiple usage of tools with grinding the edge of the tool for maybe 2 or 3 times. And it has further been mentioned that in this process the tool can only be ground for 5 times before it is finally discarded. So the tool cost comes only at the end of the 5th cycle, after 5 times the tooling has been used on the machine, and the changing time of the tool is coming out to be about 0.50 minutes. So you will have to determine the following: one is the optimum tool life and optimum cutting speed for the minimum cost per piece model, and the same for the maximum production rate model, and then some other individual things like minimum cost per component or time per component, and correspondingly the lead time, and similarly the maximum production rate or corresponding cost per component and lead time. So all these needs to be calculated from the optimization criteria which have been set in earlier. So for doing this, the first thing that we need to really mention or consider is that, let us say the first case corresponds to the optimum tool life and cutting speed so that the cost per piece is minimized. So C0, as we know, is the machine labor plus the overheads in this particular case it comes out to be 10 plus 50% of 10, and obviously that is given to be per hour unit. So if we really consider minutes as the basic unit, we divide this by 60 to find out what is per minute. So this comes out to be roughly about $0.25 per minute or 25 cents per minute, and we also are interested in finding out the overall tooling cost which comes out, which also includes the original cost of tool per cutting edge. This has been provided to be said $27.96 as illustrated in this particular data given in this problem statement. Plus, now you have to consider the grinding aspect and the number of grinds, etc. So we can say that this is grinding time times of the grinding labor rate plus the grinding overhead and if we really combine everything off here, there are about 6 times that you can use one tool. So we want to find out what is the cost per usage or per cycle. Obviously you can take one tool which is a new edge, okay, and then you are getting to use this tool 5 times post grinding. So therefore a total amount of usage of this particular cutting edge is about 6 times. So we divide the $27.96 by 6 in order to calculate the per cycle cost of the original tool per cutting edge, okay, and then you multiply this with the grinding time, which is given as in this case about 2 minutes from the data point earlier. The grinding time is 2 minutes and the tool changing time is 0.5 minutes. So here what we are going to do is to sort of calculate the overall grinding time by 2 minutes times of the labor and overhead which you utilize here. So there are exactly $15 an hour. Obviously you should divide this in the interest of making it per minute by 60, and this is what you use for every single time that you grind, okay. So the 2 minutes of grinding time with the labor and the overhead cost gives you 1 cycle grinding time, and dividing it by 60 because you want to do per minute. So therefore the overall C1 value, the cost of tooling in this particular case comes out to be about $5.16. We already know that for the minimum cost per piece model, the T minimum has been illustrated earlier as 1 by n minus 1 times of the C0 TD plus C1 divided by C0. So in this particular case the n comes out to be equal to 0.20. So we have the T minimum here as 1 by 0.20 minus 1, C0 which is $0.25 a minute plus the total amount of time per cutting edge, which in this case for unloading and loading comes out to be 0.05 minutes per piece. So we multiply that with the total time per edge 0.5 minutes and then the tooling cost which came out in the last equation per cycle as $5.16 divided by the total C0 value or the machine overhead and labor, which is in this case again 0.25. So the total time, assuming the minimum cost model in this particular case, which indicates the tool lifetime, okay. So the tool life for the minimum cost model is about 84.56 minutes. Similarly, we also have a situation where we can calculate the minimum velocity, and in this case the minimum velocity is again defined as c divided by the minimum tooling life in the Taylor equation, which has been calculated in the earlier step to the power of n. The c in this particular case has been illustrated as 200, as you can see from this tool life equation right here. N is 0.20, so we can have the V minimum as 200 divided by 84.56 to the power of n, n is 0.2. Remember, why we are converting everything into minutes is because the tool life equation also needs the time to be in minutes as per the empirical derivation which had been earlier proposed by Taylor. So therefore, we have to convert from hours to minutes, because to maintain the consistency in the tool life equation. So here the V minimum then would come out to be equal to 82.337 meter per minute, and the optimum tool life and cutting speed, again to maximize the production rate, would be again done in an identical manner, where we can find out the optimum tool life and cutting velocity in maximum production rate condition as T max equals 1 by n minus 1 Td. In this case it is equal to 1 by 0.20 minus 1 times of 0.50, so it is about 2 minutes, the maximum production rate condition. And the Vmax, the velocity for the maximum production rate condition, obviously is c divided by T max to the power of n. So 200 divided by 2 minutes to the power of 0.20 comes out to be 174.11 meter per minute. So think of it that from the minimum cost model, where you are using the tooling optimally, to the maximum production model, the velocity has come down significantly, and the time really has also come down significantly per cut. So therefore, you are cutting at a much faster pace because you want to have a maximum production rate, and you are not worrying about the tool wear rate really, which is the fact. I mean, that is how the difference essentially comes between the minimum cost model and the maximum production rate model. So we are in line with that logic, that the total tool life reduces drastically, about a 40th. In the maximum production model, the tool life is a 40th, T max is a 40th of the minimum cost per piece model, and the velocity is almost about double in the case of maximum production rate model, because obviously the cutting velocity more means the maximum production rate is being obtained. So that comes to the end of this particular session, and in the next session we will take up the two other calculations related to the maximum cost per component and time component corresponding to the lead time, and then also the maximum production rate and corresponding cost per component and lead time in the next session. Thank you.